In the silent theater of the cosmos, humanity has listened for decades, straining to hear a single intelligent whisper above the cosmic static. Then, in 2020, a young intern named Shane Smith, working with Breakthrough Listen, stumbled upon something extraordinary. A faint, persistent signal from the direction of Proxima Centauri. The astronomical community was electrified. Had we finally found a message in a bottle? The signal, dubbed BLC-1, was a narrowband transmission at 982.002 MHz, a quiet, almost pristine patch of the radio spectrum. It appeared only when the Parkes telescope was pointed at Proxima Centauri, vanishing as soon as the dish moved away. This positional lock suggested a source far beyond our solar system. For a moment, the world held its breath. If this was a genuine transmission from extraterrestrial intelligence, it would be the most profound discovery in human history. The data was scrutinized with forensic detail. Could it be a natural phenomenon? Unlikely. A hardware glitch? Possible, but the behavior didn't match. The most likely culprit? Human-made radio interference. Our planet is a noisy place, electronically speaking. Still, the signal's characteristics were tantalizing. The hunt was on to prove it wasn't just us. Scientists at Breakthrough Listen began a painstaking process of elimination, checking every possible source of interference. The excitement was tempered by skepticism. Extraordinary claims require extraordinary evidence. The search for extraterrestrial intelligence had always been a game of patience and astronomical odds. Suddenly it felt like we might have just won the lottery. But science demands rigor. Every possibility had to be ruled out before we could claim contact. The world waited, caught between hope and doubt. Proxima Centauri, our closest stellar neighbor, is a small, cool red dwarf just 425 light-years away. In 2016, astronomers confirmed a planet orbiting this star, Proxima b, a rocky super-Earth about 1.17 times our planet's mass. Most excitingly, it orbits within the habitable zone, the Goldilocks region where liquid water could exist. Proxima b completes a year in just 11.2 Earth days, orbiting much closer to its star than Mercury does to our Sun. Its proximity means it's likely tidally locked, one side in perpetual daylight, the other in endless night. This creates a world of extremes, scorching heat on one side, frigid cold on the other. Yet, the discovery energized astronomers. We now had a specific nearby target in the search for life. Rocky, in the habitable zone, and close enough to study. The detection of BLC-1 years later made Proxima b a prime candidate for our first alien neighbors. The stage was set for deeper investigation. Could this world, so close yet so alien, truly harbor life? The astronomical community focused its hopes and instruments on this enigmatic planet. The search for answers had never felt more urgent. BLC-1 wasn't a message or a code, just a pure, unmodulated tone. Its narrowband nature and frequency drift matched what you'd expect from a transmitter on a moving planet like Proxima b. Natural sources broadcast over wide frequencies. This was focused, engineered. The signal's frequency drift was consistent with orbital motion, a tantalizing hint of artificial origin. The team, led by Sophia Sheik, tried to debunk their own finding, scouring data for any terrestrial explanation. For months, BLC-1 resisted easy answers. It didn't match satellites, radar, or known natural phenomena. But after exhaustive investigation, subtle hallmarks of human-made interference emerged. The signal appeared alongside other interfering signals, all likely Earth-based. BLC-1 was never detected again. It wasn't the alien message we hoped for, but it was the most intriguing SETI candidate since the WOW signal, a powerful dress rehearsal for the real thing. The search would continue, more focused and determined than ever. Proxima b remains a world of fascination and danger. Tidally locked, it endures perpetual day and night, with life possibly confined to the twilight zone between. But its star, Proxima Centauri, is a volatile flare star, unleashing powerful radiation that could strip away any atmosphere. Without a strong magnetic field, the planet's surface would be bombarded, likely rendering it barren. On paper, Proxima b sits in the habitable zone, but reality is harsher: extremes of temperature, relentless radiation, and uncertain protection. Complex surface life seems unlikely, but life is tenacious. Perhaps it could survive underground or beneath a deep ocean, shielded from the worst. The only way to know is to keep looking, gathering more data, and probing deeper into this nearby alien world. The challenges are immense, but so is our curiosity. The James Webb Space Telescope, JWST, launched in 2021, revolutionizing our ability to study exoplanets. Its powerful infrared instruments can analyze the atmospheres of distant worlds, searching for biosignatures, gases like oxygen, methane, and water vapor. ST uses transit spectroscopy. When a planet passes in front of its star, starlight filters through its atmosphere, revealing its chemical makeup. Proxima b is a unique challenge. It doesn't transit from our perspective, but JWST can still study its faint reflected and emitted light. This is like spotting a firefly next to a searchlight, but JWST was built for such feats. Early observations have already upended our understanding of the cosmos. JWST will tell us if Proxima b has an atmosphere, and if so, what it's made of. It might confirm a barren rock, or hint at a living, breathing world. For the first time, we have the tools to search for life's fingerprints on worlds orbiting other stars. The search is entering a new era. JWST also opens the hunt for technosignatures, evidence of technology, not just life. Imagine detecting artificial light on Proxima b's night side, or industrial pollutants in its atmosphere, signs of a technological civilization. These would be almost impossible to explain naturally. The search for technosignatures shifts the focus from biology to engineering, from microbes to city lights. As telescopes grow more powerful, we'll apply these techniques to hundreds of nearby exoplanets. Each is a new chance to find evidence that we're not alone. The silence so far may simply mean we haven't been looking for the right signs. The search is expanding, and so are our hopes. Even with JWST, our view of Proxima b is indirect. To truly know, we must go there. Enter Breakthrough Starshot, a plan to send gram-scale robotic probes to Proxima Centauri using laser-driven light sails. These tiny Starship probes could reach 20% the speed of light, crossing the gap in just over 20 years. Upon arrival, they'd capture images and data, beaming it back to Earth. Starshot is ambitious, requiring breakthroughs in materials, lasers, and miniaturization. But it's plausible within a generation. Imagine seeing Proxima b's surface, oceans, or even city lights up close. Future telescopes like LUVOIR could map exoplanet surfaces, distinguishing oceans from land. Each new mission brings us closer to answering the ultimate question. Sao Bonderestern Sea is just beginning, and our reach is growing. The next leap may be within our lifetimes. The BLC-1 signal wasn't the alien greeting we hoped for, and Proxima b is a harsh world, but this isn't a story of failure. It's progress. Decades ago, finding a planet around the nearest star was speculation. Now we know its name, mass, and are studying it with advanced telescopes. The search for life is now a data-driven science, not just a philosophical question. Every null result refines our search, teaching us what to look for. With billions of stars and planets, the odds still favor life elsewhere. We've only just begun to explore the cosmic ocean. Are we alone? We don't know. But the pursuit inspires science, technology, and wonder. The universe is full of surprises, and our curiosity is louder than the silence. We will keep listening,